A 25 milliwatt laser source was kept on for 2.5 seconds. The laser source works at a wavelength of 663 nanometer. How many photons were emitted in total? Is the first question. And the second question in this same part is, suppose I kept a monochromatic source of light operating at 250 watt and it also emitted the same number of photons, then at what wavelength should it operate? Okay, so let's begin. So first we'll solve the A part, that the laser source delivered 25 into 10 to the power minus 3 joule of energy per second, and it was on for 2.5 seconds. It worked at a wavelength of 663 nanometer. The important thing to do here is that the energy of each photon, the energy that each photon carries will not depend on the power at which the device operates. It will solely depend on the wavelength, because the energy of each photon is given by the formula E equals to Sc by lambda. So Sc is a constant, so the only variable term in this quantity is lambda. So this thing is important. So if you do energy of each photon, is 6.63 into 10 to the power minus 34 times constant into speed of light, 8, 663 into 10 to the power minus 9. You should remember that order of magnitude of nanometer, even that of gigahertz and all, for it may come. So cancel, so it will go there, it will become 17, 10 to the power minus 17 minus 2, so it will be 3 into 10 to the power minus 19 joule. This is the energy of each photon. Now what is the role of this energy given here? It is only to determine the number of photons. So if one photon carries this much of energy, then how much energy would be carried by this laser source? For that we need to find out how much energy is delivered by the laser source in each second, not in 2.5 seconds, remember, because photons are released instantaneously. They do not it does not take time to release photons. The moment I switch the laser source on, photons have started emitting, and it will emit and it will be emitted for 2.5 seconds. So in 1 second, laser source emits 25 into 10 to the power minus 3 joule of energy. So number of photons, it will be 25 into 10 to the power minus 3 divided by 3 into 10 to the power minus 19. So it will be approximately 8.1, 8.3 something. It can approximate it up to 8.3 into 10 minus 10 to the power 16 number of photons, or 8 into 10 to the power 16 photons. Okay, even if some decimal value comes, you have to approximate it to the nearest integer value. Okay, so this many number of photons were emitted, but not in total. In 1 second or in each second. Okay, so number of photons emitted in total, it will be 8 into 10 to the power 6 into 2.5. 25 8 is 200. Oh, there is a 0.1, so it will be 20. 20 into 10 to the power 16 or 2 into 10 to the power 17 photons were emitted in total. For being operated in 2.5 seconds. Okay, so let's come to the second part of the question. So the second part of the question says that another monochromatic source of light is operating at this power and it is emitting same number of photons. So at what wavelength should it operate? So basically from what you did in the first problem, you have to do exactly the reverse in the second problem. So let's do it on the next page. Generally, if you do such things in exam, I prefer that you make a line here and do here some part and here some part, because while turning over the pages, usually calculation mistakes may happen, and in this part it will be compact and easy to visible. But here I am doing like this. Okay. So we have number of photons 2 into 10 to the power 17. The energy that the monochromatic source of light delivers per second is 250 joule. You can write watt as like this also. So energy of each photon, total is the B part. Okay. Total energy divided by total energy of source divided by number of photons. Wait, I was about to do a big mistake here. 2 into 10 to the power 17 is the number of photons emitted in 2.5 seconds. But here I am taking the energy that the monochromatic source delivers in each second. Right? So let me go back and read the question. How many number of photons were emitted in total? Okay, so this is the number 2 into 10 to the power 17. This much photons were emitted in total. Suppose a monochromatic source of light operating at this much power emitted same number of photons. Now this is a bit ambiguous, that what is meant by the same number of photons and at what wavelength should it operate. Okay, so what I will do is that I will take out the number. I will try by two methods and check. At first, what I will do, I will take out how much energy is delivered in 2.5 seconds divided by this number. Then this much energy divided by the number of photons that are emitted in each second. That I will find out, and in both cases I will match. Ideally, I think the answer should come same, but let's see. It will be an interesting job. Okay, so I'm doing rough only in two sides. The first side's energy of each photon denoted by E. So 250 divided by 8 into 10 to the power 16. So So 31.25 10 to the power 10 to the power minus 16 minus 17 joule. This is the energy of each photon. And what will be the wavelength? So this also you should remember. So it will be 6.63 into 10 to the power minus 34 times 3 into 10 to the power 8, 3.12 times 10 to the power minus 17. So approximately it will be 1.04, and when you divide it by 6.63, nearly it will come 6 only, I think so, because it will not make an effect if you round it up then to 2 decimal places, then it will be 6.6 divided by 1. So it's 6.6 into 10 to the power minus 17 plus 8, it becomes 10 to the power minus 9. So 6.6 nanometer. At this much wavelength it should operate. Okay. Now the energy that it delivers in 2.5 seconds. So that's simple. E dash, let it be 250 into 2.5, right, divided by 2 into 10 to the power 17. So 10 25 square 625 divided by 2 into 10 to the power minus 17, which will be 312.5 into 10 to the power minus 17 joule, or 3.125 into, I have made some mistake here, I guess. Or both should come same. Calculation mistake. Let's see. 31.25 into 10 to the power minus 16. The point will go to the left side. That means in minus the order of magnitude will increase. Okay, this seems okay. So this is also fine. Now this part, 10 to the power minus 17. So here the order of magnitude seems to be increasing. It will be 10 to the power minus 19 joule. Okay. So energies don't match, or they match. Now I should be in a position to give you a better theoretical answer. I expected that it should match, but let's see. So don't need to do the calculation further. We just note that it will the new lambda will be 6.6 into 10 to the power, so it is minus 9, so divided by minus 2, it will be minus 7 meter. 6.6 into 10 to the power minus 9 meter. Okay. So if you have conflict in the two cases, I prefer that you use this method, because it seems more accurate to calculate the per second value right, and give this is the answer. So I hope that I will try to update my knowledge and give you an answer in some post or a following video, that whether this should come same or different. Okay. So in JEE Mains and Advance, if it is an MCQ question, then definitely you can check the options, and I expect that in the options such two options will not be given. So check it. Sorry. In exam you can check the options easily and give the correct answer. No need to do brainstorming. Okay, so next question. Okay, let me pause the video a while. I will write the question.